All right, now in the second part of this, we're going to actually practice some problems that are about what they say here, how to write each series using sigma notation or the summation notation. Now, what you're going to try and do is you're going to see a sequence. This is a sequence that you're looking at right here. And you're going to try and find some way to write that particular sequence in sigma notation. So what you're really trying to come up with right here is like, where should the actual sequence start? Where should the sequence end? And what should the explicit formula be for that particular sequence? Now, it looks like to me like this particular sequence definitely is starting at 1, which would be a sub 1. So it's starting at the first term is 1, and then it goes 1, 2, 3, 4, 5 terms in. So the very first part you want to recognize is how long is the sequence that you want to sum up. In this particular case, it's 5 terms. So I'm going to start my sequence with, and you can use n or you can use x. It doesn't really matter. Sometimes you will see them written with i's. That's okay too. It's just a variable. I'm going to start saying that this sequence is going to start at term number 1, and it's going to terminate by the time it gets to number 5. Okay. Now, what the hardest part about writing these summation notations is really coming up with what goes in this location. What is the equation that is going on right there? What equation should I be putting in that location that would generate these terms going down the line? Now, in a lot of ways, these kind of questions are kind of like hide and seek. All right. I know I love hide and seek. And what I mean by that is that you have to actually look at the pattern yourself and try and find some way to discover what is causing that pattern to take place. Now, a couple of things that you might look for. Okay, some things in this hide and seek pattern that can be helpful are things like, is the thing going up by addition or subtraction? If that it's in an arithmetic one where it adds by a certain amount, that might help you determine how to write your equation. Sometimes it helps understanding whether or not the equation or the sequences are going up by multiplication or division too as well. That'll help you kind of get yourself guided in how to write the equation. Now, there are other ones in there that are kind of harder to see and harder to find. And that's specifically things like powers, like know your powers. Like when you recognize a pattern like 1 and 4 and 9 and 16, you recognize that that is a pattern of squares. All right. So powers or squares or cubes, they all tend to be something that can be used in terms of writing the formula. And the last one is kind of the innocuous ones, which are the factorial concept. Maybe you know how to think about how factorials work, like 1 factorial is 1, and 2 factorial is 2, and 3 factorial is 3 times 2 times 1. Oh, that's 6. And whoa, wait a second. 1, 2, 6. That kind of looks like what I've got written right there. Ooh, hide and seek. I love it. Answer n factorial. That's the one that's being listed in this particular case. Now, people would have looked at that thing probably until they were cross-eyed, but by recognizing that there's some other patterns out there, you can do that. Now, I'm going to put a fifth one on here. Sometimes the patterns are not in one of these categories. Sometimes they fall into a category called recursive formulas. And I'll talk about recursive formulas in the next section and how they work, but we'll get there. Now, if I start looking at some of these, we can probably recognize patterns. We've got 1, then 2. Okay, now that looks like 1 squared, and that looks like, 2 squared, and that's 3 squared, and that's 4 squared. Hey, I think I got it. 1, 2, 3, not 4, it's squared. So I must be writing that the sigma in this case, starting in the first term, is going from x equals 1 to 7, because that is 7 squared, and that must be x squared. That's what we're going to write as its summation notation. Okay. Now, some summation notations can be a little bit hard to identify. like you're looking at 2, 4, 6, 8, 10. You're like, oh man, I know that this is term number 1, but what would I have to do to the number 1 to make it become the number 2? Well, I probably would take the number 2 and I'd multiply it by 1. That would give me 2. And then this would be the second term, which they'd be plugging in 2. Maybe I would take 2 and I would multiply it by 2 and I would get 4. Oh, there's my pattern. Summation notation on this would be from x equaling 1 to, I don't know, that's 1, 2, 3, 4, 5, 6, 7, 8. 8 terms in. And it would be 2 times each one of the integer values, oops, not 1, x is what I put right there. And that would be the summation notation that would generate this pattern. Okay, now each one of those is a little bit of seek and find. Don't be discouraged. Sometimes they can be really hard and they take you a little while to figure them out. Now, some other little patterns that you kind of want to recognize is like number 10. How do they get this alternating sign to take place? Well, first off, let's deal with where 1, 3, 9, 27, and 81 come from. Well, that is 3 to the first. Well, and that's 3 to the second, and that's 3 to the third, and that's 3 to the fourth. And, ooh, that would be 3 to the 0. Well, one of the notations you could write here with this particular signal would be something like, I'm going to write it with an I just so you're aware of that. This sequence doesn't start at 1. It's starting at 0 term. Well, you could call a sub 1 being the term you're at, but the term that came before it would be a sub 0. It would be the one that just came before it. So if I said this one started at 0 and went to 4, what would I write it as? Well, the same thing is saying the same here. It's just the numbers being plugged in the top. That would be 3 to the I. Now, we usually don't like to write our summations with a 0 in the bottom. 0 and 1 are probably the most common, but 1 is what we really prefer them to look like. So if I was going to change this to I equals 1 to 5, how would I have to change the format inside here? Well, I'd only have to make one small adjustment. 3 wouldn't change, but instead of this being I, if I was plugging in 1, I still want it to be 0. It would be I minus 1. And then I would get the same exact sequence over again. Okay? This is the preferred way to write your sigmas. Now, when you guys do this in Math Excel, be very, very careful. Read the directions when you do it so that you don't make those mistakes. Now, in terms of like sine and cosine, oh, it looks like the same thing as sine, 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 sine. Oh, it must be sigma about sine is what it is, and it's going from 0 to 4. Now, I don't want to write it as 0. Maybe I should write it as x from 1 to 5 because there's 5 terms, but I would put inside here x minus 1 so that I would generate the very first term. Okay? Now, as we go down some of these, you'll probably recognize other little patterns like 3, 6, 9, 12. Oh, that must be a multiple of, that's a multiple of 3 somehow. And that would be 3 times 1 and 3 times 2. You kind of have to break them down and be like, oh, where did they come from? 3 times 1 and 3 times 2. Okay, something like that. 3 times 3. Oh, that must be easy. Sigma is from n equals 1 to, now wait a second. This doesn't have a 2 part to it. You're like, what the heck does that mean? Well, that means that that sequence goes on forever. So that would mean that the upper range of the sigma is infinity. It goes on forever. And the notation here would be 3 times each term times, oh, it's 3 times n. And that would be the summation there. Now, it would make sense that you would probably be like, man, if I sum together all the numbers of 3 times to infinity, it would be infinity. And you're right. The answer in this case would be infinity. It would just never be an answer that it could be achieved. But there are certain sequences that have infinity as one of their extremes, and they end up condensing to a number. No, welcome to calculus. That's going to be one of our ideas there. Okay, 2, 5, 10, 17. I don't know. Do you guys see a pattern there? Maybe it's got something to do with squares. Oh, wait, that I kind of see like 9 right there, and this is 16, and that's 25. Oh, it's one more than the square that's already there. So it's kind of like we squared the value and then we added 1 to it. Oh, all right, let's try that out. Sigma of x squared plus 1. And then I started at 1 and I ended at 6. And that gave me the sequence that's going on there. Okay, let's see if we can discover number 14. 14. I'm gonna pause right here. You guys think about what you think it might be. So what I did was I wrote a couple of numbers underneath, and I was kind of like thinking about how they're related here, and like 2 times something, man, and this one times something. I wonder if I multiplied this by 3, it'd be the number 21, and then it'd be 2 too many. If I multiplied this by 3, it'd be 6, and it'd be 2 too. Oh, maybe that's what it is. I need to take the concept, multiply it by 3, and then take that number and subtract 2 from it. And that would give me the sigma that I'm talking about. So x is equal to 1 to 7. Now, guys, don't be disheartened. Sometimes these sequences are really hard to come up with an explicit formula. It's about trial and error, and you got to keep trying for it, okay? The next sequence right here, if you pause the video, you can try it on your own, and then I will show you what it'll end up turning out to be. I'm going to choose n equals 1. This goes to infinity. And the sequence on this one is 2n minus 3. You have to double the number and then subtract 3 from it. So kind of look at like how you're going to adjust it before you do it. Now, there's some really challenging ones down below, and I'm going to get these done in the next 3 minutes. So keep in mind that I'm going to move kind of fast here. I'm going to go with this one right here. It says 1, 2, 6, and 24. And there's 4 terms there. So this sigma must go from x equals 1 to 4. And I've seen the 1, 2, 6, 4, 6, 24 pattern before. That was a factorial. And that takes care of the front. Now, if I do that as one of the terms, then I would do the other one at exactly the same time to get the next one. Now, that is 4 to the first power, and that is 4 to the second power. Oh, there it is. 4 raised to the x. And you got yourself a little bit more complex pattern. But it's basically broken down into 2 separate problems. Now I'm going to put all the division lines inside this one. And I'm going to say that goes from term number 1 to term number 7, because 1, 2, 3, 4, 5, 6, 7. So this must be a sigma from 1 to 7. But what would the formula be? Well, it's got to be divided by 3, because that's all the same all the way through. It's really the top that is going on something different there. And each one of those is 1 less than its square. Sometimes you got to look at them real close before you see it. So that would mean I must square it, and then I would take away 1 from it. And that would give me the answer that's in the numerator. This last one down here at the bottom, this one happens to come from an idea called Pascal's triangle. And it's about permutations and, most importantly, combinations. These are a combo deal. And this one happens to be a little quirky. That's 1, 2, 3, 4, 5. So x equals 1 to 5 of a combo deal. And this is how many different ways that you could like choose cards from a deck of cards. So if you had 5 cards and you had to choose all 5 of them, you would only do it one way. But if you had to choose, or if you choose none of the cards, there's only one way to do it. You choose 1 card, there would be 4 different ways you could choose the deck. So this is about 5 choose. Is it 5 or no? It's 4. So this one is going to start. It's a little bit bizarre because when you do chooses, that's not even a word. It starts at 0 and it goes to the term. So this is 0 a sub 0, and this one is a sub 4. It's just that the way that one works out. So this would be 4 choose. And this, we'll see some of these later. 4 choose x. Now, if you wanted to make that particular sequence based on 1 to 5, I'll see if you guys can figure it out. And the sequence you see right there is the way you would write it as 1.